Hello, Rama. Let's draw the Bornholm cycle of MgBr2. Right? Okay. So when drawing the Bornholm cycle, we are supposed to start with the reference forms, the reference forms of the system. So our system is MgBr2. So the reference forms are the magnesium solid and the Br2 liquid. The bromine appears as a liquid at normal conditions, right? So let's start with that, the reference forms. So let's start with that. Reference forms are magnesium solid and Br2 liquid. As our system contains one magnesium atom and two bromine atoms, these are the reference forms of the two types of component atoms, right? And one magnesium and two bromines are represented here, right? So reference forms are written. Then we need to come up with the solid ionic compound at here. Solid ionic compound, right? The second thing to draw. So that is magnesium bromide solid. Right now, this is referred to as what? This is referred to as the enthalpy change of formation. From the reference forms, you are producing the compound you need. Delta H naught F value, right? Right. The third thing to draw is copy the constituent gaseous signs. Constituent gaseous signs. So with the magnesium bromide solid, the constituent ions are Mg2 plus, Mg2 plus, and the Br minus, Mg2 plus, and the Br minus, right? So in the gaseous form, gaseous state, right? So Mg2 plus ion in the gaseous state and Br minus ion in the gaseous state, right? And two of Brs are needed, Br minus are needed, so two of Br minus, right? So each and every state of the same system should be mass conserved, right? Two of Brs are needed, two Br minus. So this is related via the lattice formation enthalpy. We have lattice formation enthalpy, right? So with the constituent gaseous ions, you are forming the solid ionic lattice one more. So that is lattice formation enthalpy, right? Okay. The negative value, right, for lattice formation. Right. Now we need to connect this state to this state. For that, we may have to use numbers of enthalpy changes. Just do those, right? So our task is to convert this magnesium solid first to magnesium plus gas, and then we need to convert this Br2 liquid to 2 of Br minus gas, right? These are two tasks to complete. First, let's convert this magnesium solid to magnesium plus gas. So ionization should be done. Enthalpy change of ionization should be done. The first ionization as well as the second ionization, right? To do ionizations, first you need to come up with the monoatomic gaseous forms. Monoatomic gaseous forms, right? So by only with those you are able to do the ionizations as well as the electron gains, right? Okay, so let's copy the monoatomic gaseous form of magnesium solid, right? So for that we can do few changes, right? Few enthalpies can be used to copy the magnesium, right? Monoatomic gaseous form, magnesium gas, the monoatomic gaseous form. Right? To do this conversion, to convert magnesium solid to magnesium monoatomic gaseous form, right? We can copy the atomization, right? The reference form will be converted to, right, single 1 mole of elemental gas molecules, right? Elemental gas atoms, right? Atomization can be done, or you can do the sublimation. Or you can do kind of a fusion and then the, right, vaporization. So let's come up with delta H naught atomization, or according to the data provided in the question, you can use delta H naught sublimation as well, right? So we had produced the magnesium gas. Then we need to convert this into +2 gaseous form. But first of all, you need to come up with the +1 gaseous form, right? That can be done with the use of a first ionization. Use of first ionization enthalpy, right? So that will produce the magnesium plus gas and an electron. So Br2 liquid appears as it is, right? So this change can be done with the use of a ionization, first ionization, delta H naught I1. So one can say IE1 no, I1 no worries, right? First ionization. Next, right? We need to come up with the Mg2 plus gas, right? So then the second ionization could be carried out, right? Okay. So that will produce the magnesium 2 plus gas, and as another electron is released, that electron and this electron gives you 2 electrons, right? So this change can be done with the use of second ionization enthalpy of the magnesium I2. Clear? Right. Next, now the things with the magnesium is done. Now we had converted the magnesium 2 plus gas, that is done. Now what we need to do is converting this Br2 liquid to the B2 of Br minus gaseous signs, right? Okay, let's start that process, right? So we can first actually we need to do some kind of a electron gain to come up with the Br minus gases. To do electron gains, first we need to convert this into monoatomic gaseous forms, right? So let's do this stuff, right? So converting this into monoatomic gaseous forms, that is what we are doing first, right? Okay, that can be done. So keeping these two guys like as it were, right? We need to convert this into monoatomic gaseous forms. That means we can convert this into 2 of Br gases. Monoatomic gaseous form, no? 2 of Br gases, right? So this can be done with the use of atomization. So this is the reference form of Br2. So with the use of atomization, you can convert that into monoatomic gaseous form, right? Atomization of Br can be done, and if you do the atomization, you need to produce two of atoms. So you need to provide the heat change twice. Starting from the reference form, you need to produce 2 of gaseous atoms. So atomization should be done twice, right? Okay. If you are thinking of bond dissociation, if you are thinking of going through the bond dissociation here to produce the monoatomic gaseous species, right? If you are thinking of going through the bond dissociation, first you need to convert this into the gaseous form. First you need to convert this into Br2 gas. To convert this into Br2 gas, right, you need to first do kind of a vaporization, evap should be done. Why? Because you can't do bond dissociations, right, when you are with the liquid form. Bond dissociation involves gaseous bonds to break. Bond dissociation means that, right, it is the enthalpy change needed to break 1 mole of gaseous covalent bonds to come up with monoatomic gaseous forms, right? So first you need to convert this into the gas state to come up with Br2, these gaseous bonds, right? So that then only you can use the bond dissociation, right? So first we need to convert this liquid to gas. That can be done by the vaporization or evaporation, right? And then you can apply the bond dissociation of Br1. Right now, the thing is clear. That is how, right, we are supposed to, right, convert this Br to liquid to two of Br gases. You can directly supply two of deletion or deatomization, or you need to first complete the vaporization and then some bond design is needed. Right now, so like that we can produce two of Br gases. Now what we need to do is just convert this two of electrons and two of Br gases to two of Br minus gases, right? So that can be done easily by supplying the supplying the electron gain enthalpies, right? So converting a Br gas to Br minus gas, you need to supply the electron gain enthalpy change. So the first electron gain, as we are supposed to produce the minus 1 gaseous ion, and now we need to produce two of those ions. To provide one of the ions, you need to supply this enthalpy change, but to produce two, you need to supply the enthalpy change twice. Right? The idea is clear? Right. This is going to be the Born-Haber cycle for MgBr2. Right? They will provide you one of these data, right? If they will provide you this data or this, right? One of these will provide. So you can use, right, the given data respectively, right? Okay, so that is the Born-Haber cycle for the MgBr2. So let's complete the stuff by applying the Hayes law for this thing, right? Applying Hayes law, right? Applying the Hayes law. It means this is the first route. This is the first route available to go from initial to final states. This is the initial state. This is the final state, right? So this is the first route available. So deletion of is going to be equal to the summation of enthalpy values of this second route, right? So starting with this, I'll go with some sublimation here, plus this thing, right? Ionizations, then this one I'll go with atomization in this case, and then two of electron gains are there. Finally, the lattice enthalpy, that is formation enthalpy. So this is the relationship between the enthalpy terms appearing with the Born-Haber cycle of MgBr2, right? The thing is clear. So complete the stuff. Then we have to do the calcium iodide thing as well. So first complete the stuff. So start drawing the Born-Haber cycle is always with the reference forms of the system. The system is all about the calcium iodide CaI2. You are with one calcium atom and two iodine atoms in your whole system, right? So start with the reference forms of the system. So calcium, its reference form is calcium solid. All the metals appears as solids, right? And iodine, its reference form is I2 solid as well, right? When it comes to halogens, all the halogens appear as diatomic forms, right? I mean I2, Br2, Cl2 like that, F2. But when it comes to fluorine and chlorine, those appears as gases, and bromine is a liquid, and the iodine is a solid at room conditions, right? Okay, the reference form is I2 solid for the iodine, right? So let's start with the reference forms, right? Okay, this is the first thing to do, right? Starting with the reference forms, right? So calcium's reference form is calcium solid, and the iodine's reference form is I2 solid. So this represents one calcium atom and two iodine atoms, which should be there in your system, right? That is clear. Then second thing to do, write in the solid ionic lattice. Right? Solid ionic lattice. It is what? It is calcium iodide. We are referring here. Calcium iodide Ca I2, no? The solid ionic lattice, right? This is related by what? This is related by the formation enthalpy. Reference forms are converted to 1 mole of corresponding compound, corresponding species. That means it is all about the formation enthalpy. Right? Okay. Next thing to do is draw in the constituent ions of this solid ionic lattice, but in the gaseous form, gaseous state, right? So the constituent ions are calcium 2 plus, and the I minus, and the calcium 2 plus. So those should be at the gaseous state, right? So calcium 2 plus gas and I minus should be at the gaseous state, and 2 of I minus should appear to the conservation of mass, right? Now, so our task is to now to convert this calcium solid to calcium 2 plus gas, as well as to convert this I2 solid to 2 of I minus gas, right? Now, okay, let's start with the conversion of calcium solid to calcium 2 plus gas. So definitely we need to go through ionizations to come up with the right ions in the gaseous form, right? So to go through ionizations, first we need to come up with the monoatomic gaseous forms. So this can be converted to monoatomic gaseous forms by doing some atomization enthalpy as well as some sublimation. So fusion followed by vaporization, right? Let's do one of those, right? Right. So we are coming up with calcium gas with I2 solid, right? This change could be done by applying the atomization enthalpy of calcium solid, or we can apply the sublimation enthalpy of calcium solid. According to data given, you have to decide, right? Or we can apply the fusion plus the vaporization. This also can be applied if the data are given like that, right? Okay, right. Then what else? So we had converted the calcium solid to calcium gas. So we need to go towards here. So now we can apply the ionization enthalpies, because now we are with the monoatomic gaseous form. So we can convert this calcium gas to calcium plus gas by releasing one mole of electrons like this. The I2 solid still appears as it was right there. So this change can be done by applying the right ionization, the first ionization of calcium, I1. So you can convert this into plus 2 gas as well by applying the second ionization, right? Okay. So when the second ionization is applied, another electron is released. So that electron and this electron means 2 electrons, they are at this state, right? This is all about the I2 second ionization, which interchange of second ionization. Right now? Okay. Now we are done with the calcium 2 plus, right? we are happy. Then what we need to do is we need to convert this I2 solid to 2 of I minus gases, right? So first of all, we need to come up with the gaseous state. We need to come up with the gaseous state, right? So how to come up with the gaseous state there? How to come up with the gaseous state? First, the liquid should be converted to gaseous state, right? Because to come up with the monoatomic gaseous forms, we need to come up with the monoatomic gaseous forms, right? To do kind of a electron gain. So electron gain is needed to form the minus ions, right? So to come up with the monoatomic gaseous forms, first we need to convert this into gas, right? So that can be converted to gas by applying a sublimation. Sublimation here. Sublimation here. Or as this reference form is available, you can directly convert this to monoatomic gases by atomization, right? So we can do a few things, right? I'll write it here. Right, to convert this thing, right, to two of I gases, right? Few things could be done. One thing is just the atomization. Starting from reference form, just to do the atomization. That means two of atoms are to be formed, so delta H naught D atomization, right? Or else, or else, if you are trying to go to a bond dissociation, if you're trying to go to a bond dissociation, first of all, this should be converted to the gaseous form because bond dissociation will be done by breaking only the gaseous, by breaking only the gaseous covalent bonds, right? So to convert this into gaseous form, first we may need to do the right sublimation of I2, and then you can do the bond dissociation of I2. Right now, thing is again, first you need to sublimate the stuff to come up with the gaseous form, then only you can do the bond dissociation, right? Because bond dissociation should be done, right? After bond dissociation could be done only with the gaseous species, right? So first need to convert it to gaseous form. That can be done with sublimation, then the bond dissociation, right? That will provide you these two of iodine gases. By breaking one of the bonds, it will provide you two of iodine gases, right? Okay, so that thing is done. So final state. Now you can convert this two iodine gases and two of electrons to two of I minus gases, right? So that thing can be done with the use of electron gain, right? It is forming the first minus ion, so it is the electron gain 1, and we need to form, as we need to form two of I minus gases, so we need to provide this electron gain 1 energy twice, right now. Okay, now, right, that is the idea there, right? So this final stuff is, I have not written this thing. This is actually what? This is lattice enthalpy, right? Clear, no? That is formation enthalpy. Right, now we can apply the His law to come up with the relationship among these species, right? So just apply the His law. Right? So it says this is the first root, which means if to go from initial to final, this is the initial state, right? All that will start from here, this one, right? And this one is the final state, all that was coming towards here, right? So To go from initial to final, this is one route available, this is the other route, right? So the different if is equal to summation of enthalpy values of the second route, right? So I write only one of these things, right? It's come the atomization plus this one I2 and this one, right? This can't be the atomization. Two of those things should be done as you are to produce two of I gases, right? Then two of electron gain one, and finally that is enthalpy. Right? That is the His law, right? So this is all about the Born-Haber cycle of calcium iodide. Clear? Let's complete this stuff. So that is all I am to discuss today with this short session. So you have another homework about the Born-Haber cycle of aluminum oxide. Just do that at home, and we'll discuss that thing at your class. Goodbye.